Thank you so much. Thank you everyone, and especially my sincere thanks to theoretical and practical perspectives in GFD group. Special thanks to Jim and Manita and all the persons, and thanks to ICTS for arranging this kind of talk. So my name simply Raja. I am from one of the IITs, is on the east coast of India on the top side, near to Bangladesh. I work there, and so good afternoon everyone, and today I'm going to talk about these large scale vortices in oceans. So we have seen very interesting talks on GFD, very rich in terms of oceanic studies, and here what we are trying to see is something like a toy model to understand such large size vortices, small size vortices, how do they interact with each other, how long these large kind of things survive, how long these small things survive, whether these mid-latitude kind of vortices are stable compared to large size equators, near equator zone vortices. This is the talk all about. And is there a way I can really construct a simple scaling theory based on counting number of vortices and their size? If I know vortices number depends on the area, a distribution kind of thing, can I construct energy entropy kind of cascade? That's the whole point of today's talk. So before jumping into that, I just would like to remind you, the big picture what we are seeing is NASA's virtual ocean. Just to appreciate these vortices and their size, so typically geophysical kind of dynamics, 3D, but under certain approximation, one can really pretend that these are two-dimensional kind of systems, the geostrophic kind of nature. And what we can see is something like circulating kind of portion, some kind of straining zones. These are what people call filamentary kind of structures, fronts, and so on, so things. But predominantly what we see is vortices goes around entire this ocean. And what exactly these dynamics, how long do they survive? That's the thing what we are going to look at. Okay. So just to begin, there is a map, mean radius of these vortices in logarithmic scale, near the equator, very large size kind of vortices, and as we are going away from equator towards mid-latitude, their size decreases. Similarly, out of 28 days, nature, if we are going to really look at how long these vortices really survive, most of the equator zone things dies away, but mid-latitude kind of thing, in some sense stable, and you will find it for a very long time. And similarly, the number of vortices, if we are going to look at per square kilometer, these dots what we are looking at is per 1 kilometer square each dot represents. Mostly we see a lot of vortices away from that mid-latitude. And this kind of thing to understand, one of the crucial important parameter is Rossby radius, and which will be varied along this equator to mid-latitudes. And what we try to do is try to simulate this freely decaying quasi-geostrophic turbulence. So typically quasi-geostrophic turbulence, this kind of flow fields, if we are looking at that, weakly non-conservative systems, or possibly they mimic in some sense conservative kind of systems. Because of that, we don't really look at viscous kind of actions during our simulations, give some initial energy on the wave numbers, how these vortices really evolve, how coherent vortices really develop, how they really grow and die. So this entire work done by Krishna, she is a PhD scholar. I work with her, and she asked two important questions for this quasi-geostrophic turbulence. How do these coherent vortices really develop? And what is the connection with energy spectra? And which vortices out of all these things drive the entire system? Do I need all these things? Or I can chuck out some of the things, but still spectra remains same. Using complex networks, she tried to understand what are the prominent important vortices in the system. And usually these ranges, few hundred meters to something like few thousand kilometers they will have, and 40% of the kinetic energy contained in these large scale structures. So the story entirely dates back to, inspired from Kolmogorov theory in 3D turbulence, where under inertial range, if something like highly inviscid kind of limit, if we are looking at that, energy spectra can be remarkably talked in terms of structure function to spectral space as k power minus 5/3. Inspired by that, Kreischer and Batchelor try to really look for 2D kind of turbulence, try to come up with something in the inertial range. It may have k power minus 3 kind of spectra instead of minus 5/3. But later on, 1980s, 1990s onwards, McWilliams is one of the giant in this quasi-geostrophic turbulence, try to come up with this idea on coherent vortices. When you have coherent vortices, this Kreischer and Batchelor spectra may not work, and you will have higher spectral slope more than k power minus 3, maybe k power minus 4, k power minus 6, this kind of things happens. And the question is, how to really understand that spectra, steeper spectra in the system. Just to give overall introduction, in 3D turbulence, if we are looking at that, the kinetic energy balances with entropy via viscous terms, and usually what people realize, if viscosity is very small, maybe dE by dt tends to 0, but at the same time, because of vortex stretching terms, this entropy unboundedly grows, so this entire limit turns out to be a finite limit, and people call it as dissipative anomaly. So entropy can unboundedly grow inside 3D systems by stretching more and more intensified vortices happens. And based on the arguments, one can really show that dimensionless arguments, how these third order structure functions, second order structure functions, which are kinetic energy representation in terms of energy spectra for 3D under self-similarity and inviscid limits. The same thing, if one would like to really understand a 2D geostrophic kind of turbulence, the easiest way to understand is, we will always have wall friction, earth might be spinning, so friction will be there, Ekman layers and so on. One can pretend that it is more like Z square kind of thing, convert 3D into 2D kind of thing with additional friction terms, so that instead of understanding 3D turbulence, 2D turbulence with additional frictional terms like Ekman, Rayleigh, Hartmann, or whatever the kind of friction. So one can establish 2D kind of fields to understand this turbulence dynamics. And in this kind of 2D turbulence, there always be invariance when viscous or frictional kind of things are going to 0, energy and many more kind of invariance exists. One of the invariant, what we call entropy in the system. And in 2D turbulence, the most important thing is the palentropy term, which connects with entropy evaluation, always be positive definite. So this term always decreases with the time. The entropy decays down with the time. It never unboundedly grows like 3D turbulence. Because it is going to decay down and has a bound, this dE by dt under viscous limit, even though nu tends to 0, this Z is bounded, dE by dt possibly turns out to be 0. So energy conserves are weakly a kind of conservative systems one may be in a position to really sense. And with that inspiration from K41 kind of thing, first Batchelor has attempted try to get in terms of structure functions for velocity and also the entropy kind of thing. Figure it out, there is something like direct entropy cascade happens at higher wave numbers, and something like inverse energy cascade, like more and more bigger structures develops at smaller wave numbers. And Kreischer, what he has realized, there is some problem with Batchelor scaling in terms of k power minus 3. It requires corrections, proposed logarithmic corrections, and still found this kinetic energy spectra goes like k power minus 3, logarithmic corrections. So whole focus is whether it really shows k power minus 3 or more than that. Though by dimensional arguments, one can really deduce this kind of thing. When people really went with the simulations, what they realized was that inertial range never showed k power minus 3, always be higher spectral thing content what they have seen. And even when one has this barotropic kind of turbulence, under time and this barotropic kind of nature, one can really get a self-similar kind of nature in terms of energy spectra under proper scaling. Try to sense that possibly steeper spectra compared to Batchelor and Krishnan spectra in 2D. So basically, KB theory says k power minus 3, but the typical simulation shows that 4 to 6 kind of exponent in the inertial range of this direct entropy cascade for the energy. And what we try to figure it out, is there a way I can really understand the spectral by knowing about the dynamics of vortices, how do they interact with each other? And can I really come up with a simple theory? So the quasi 2D geostrophic turbulence, the important parameters are inverse Rossby radius, in some sense Coriolis to gravitational stability kind of thing, potential vorticity in terms of vorticity with this stream function, and the governing equations are how this potential vorticity evolves over the time. Because it's nearly conservative systems what we are trying to look at. We do not have direct viscosity, but we want to take out energy at smaller scales so that more and more smaller scales can be halted. So everything we would like to really look at higher cascades. The important quantity to be measured are energy. So energy, kinetic energy at a particular wave number, and entropy, so at a particular wave number. These are the two important quantities one can really measure. And try to do it in double periodic kind of systems with different grids like 512 to 4096 with broad range of initial kinetic energy we put. So something like taking a domain, each and every point has certain energy content in the system. It looks like random, but a lot of kinetic energy and vorticity present on that system. And we evolve from that state. And typical Reynolds numbers based on these integral scales and how much initial kinetic energy we put in is around 10 power 4, which used to be moderately high Reynolds numbers. And try to play with this inverse Rossby number 0 to 70. Typically 0 means 2D kind of turbulence, around 20 is more like mid-latitude, 20 to 40 kind of thing is mid-latitude kind of zones. And if we do the simulations, so the initial state, this is 2D turbulence going towards the mid-latitudes, is more like toy models, what we are trying to look at. Larger and larger scales develops, monopoles will be created, and these either positive or negative kind of things breaks and create filamentary kind of structures, and possibly they grow in size. When we are going towards mid-latitudes, they grow in size, but it looks like more quasi-frozen kind of crystals. And these are highly dynamic in nature, but these are highly stable in nature. So this connection, what we are trying to look at later, why mid-latitude vortices are more stable and interconnected with each other. If you remove one of the vortex, it can really destabilize the entire system. But here, unless you remove that bigger one, it hardly affects the entire dynamics. So via these complex networks, we will show that these are robust compared to this. So near equator, there are monopoles grow widely spread, broad range in size, but near mid-latitudes, quasi-frozen, near to each other, nearly uniform kind of vortices one will see. Yeah.
Go back to the equation. You're saying the
kind of thing by toy model. Oh, this is F-plane based localized turbulence. I can't apply. So it's a toy model just to pretend what is happening in the system. So we take initial potential vortice in the system, symmetric kind of thing, try to look at extreme events out of the system, look at different lambda values, and look at how these extreme events grow in the system for two different kind of times. There will always be super exponential kind of things. But if we are coming towards this toy model latitudes, mid-latitudes, they becomes exponential to Gaussian kind of potential vorticity, one will be in a position to see. And then we try to extract this vortex information, especially discarding entire information via vortex criteria, and try to understand how the number of vortices go with the time as we are going away from lambda. And basically, that shows two different power law behaviors. The number of vortices decreases with the time, and the average radius of these vortices increases with the time. And they show one particular number, the particular number like 0.36, 0.18 kind of things. And these numbers are typical 2D turbulence kind of state. From there, they either quickly grow or quickly decay kind of thing happens. And most of the energy potential entropy contained in these vortices. And that's the thing what we try to really realize. Then we try to come up with why that kind of spectral slope really comes out of these vortices. So first separated out these vortex populations based on their area, counted number of vortices, then using centered values, potential vorticity separated, then calculated average potential vorticity on that system via populations and also kinetic energy spectra. Then any area is proportional to wave inverse of this wave number sphere. So equating this potential vorticity extracted on vortices, 2 more minutes we are done. And then calculated this kinetic energy spectra. And that what we realize is it depends on number of vortices and how they are connected with each other. 248, 2 more minutes. Then establish a link. What is the connection between number of vortices and area? And from numerical simulations, we figure it out. It goes like a power minus p, and p is the index what we figured out. If I know that, kinetic energy spectra can be recaptured in terms of this minus 7 plus 2p kind of thing, which will be steeper spectra compared to Krishnan and Batchelor spectrum. And numerically, what we figured out, the n of a goes like a power minus 3 by 2 near 2D or equator zones. Around mid latitudes, it goes like a power minus 1 by 2. So if we are going to plug back in that energy spectra, basically near equators, it will be k power minus 4. And as we are going away from these equators, it will be k power minus kind of 6 spectra, one will be in a position to establish. And then we went ahead further, it's about spectra, but how strongly these vortices perturb the system. For that purpose, use complex networks, degree, knottedness, and higher order kind of statistics. Realize that in 2D turbulence, purely at the equators, there are small number of hubs will be there. If we are going to remove those hubs out of the system, this entire system will collapse. It can't maintain the 2D turbulence. But if we are going towards this mid latitudes, so more and more number of hubs are most prominent influencers or vortices evolve in the system. Even if we can remove one, that can destabilize the entire system. And then try to play with how many random vortices we can really remove, recapture that entire spectra in that way. So that's all about my story. So the conclusion is, near equators, vortices are short life, wide range of scales, local interactions are possible. Mid latitudes, long life vortices, nearly same scales you will see, but non-local interactions really develop in the system. And all these things under a toy model like 2D quasi-geostrophic equation under F-plane approximation. Thank you very much. Thank you, everyone.
So we have time for a couple of questions.
That's the way traditional numerical simulation works. What we are using is complex network strategies. No, we didn't do that. Okay, the whole point is about this energy versus wave number spectra. And now via complex networks, I have identified what are the important hubs or vortices out of the system. Now take out those vortices out of the system, again recalculate energy. And the question what you are asking is quite interesting. Remove those vortices, go on evolve, what will happen to that system? That's the thing presently we are carrying out, but at this point I do not have any results on it. So it's different way of looking at stability, instabilities compared to traditional asymptotic waves or small amplitude perturbations.
Or even just a more well-headed way of just, kind of artificially
take out and
vorticity, right? And see what happens.
Surely, I will look into that. Thank you so much.
Thank you very much. Let's thank the speaker again. And